Okay, so we'll begin with the channel coding lecture. In our last class, we tried to consider uh, some techniques that could be used for the approximation of the entropy, which led to source coding. Since we've covered the source coding aspect, so it means that the compressed data can now be prepared for transmission. So say that channel coding is simply a technique used to prepare the compressed data for transmission over the channel, okay? So we already talked about source coding. We're not saying that the output we have here will now be prepared for transmission over the communication channel through a technique we call channel coding. Now, you recall that while we perform source coding, we try to figure out the optimal code, okay? And then we're able to figure out if the code is decodable, uniquely decodable, and the likes. And now we try to resolve that to avoid ambiguity in the decoder. And also, we've been able to literally compress the message data or the message bits in such a way that redundancies were removed to the barest minimum, right? And now that we have done that, relative to the capacity of the channel, we now want to encode this message symbol. And by so doing, we now want to add redundancy. Not because we are trying to complicate what we did at the source coding phase, but rather we want to now make this code robust against errors over the channel. So this is immunity against channel errors. And that's why we want to do this. So technically speaking, we'll say that channel coding is simply a technique used to detect and correct errors. Used during data transmission. Okay, so this is usually done by adding redundancy to the transmitted message, and then we allow the receiver to identify and correct the errors without necessarily calling for retransmission. Is this clear, please?
Yes, sir.
So now we'll talk about some examples. So types of channel coding. I know you already have some resources online. We already uploaded our old notes, so you want to look them up for specific details. This follows directly from the error control coding. So some of the things we're going to talk about here, you'll find in our old notes, and there are a few details we may not have documented in the online notes or in the notes online that we're going to mention in this class. So the first of these codes that we'll be talking about is the block codes. Now, this we have described extensively in our previous note, and we know that these codes operate on fixed block size of data, okay? And fixed block size. So block codes usually divide the data into fixed length blocks, and then they add parity bits for error detection and correction. So we now have something like this, where we have the message bit, say N, no K, message bit K, and then let's write this. So we have the message bit K, and having a block length is the total block length, say N, and then we add the parity, which is some value that removes the bit size from the block length, N minus K. So here, this is the message bit, and this is the parity bit. And each block is independently encoded and decoded. And we'll also have some examples, okay? Some of the notable ones are the Hamming code. We also have the Boss Kunduri Hopewell code. Then we also have the Rich Solomon codes. Okay, so we'll just introduce them briefly. So when we talk about the Hamming codes, well, they are suitable for literally detecting 2 bits error. They detect 2 bits errors, and then they correct 1 bit error. Okay. So in designing such codes, they are designed in such a way that the redundancy is minimal. Okay. And then they also use parity bits that are placed at positions, you know, that are powers of 2. So the number of parity bits needed to be determined will now be in the order of 2 to the power of R greater or equal to K plus R plus 1. So in this case, we already know that K is the message bit, and R is the number of redundant bits. So if, for instance, we take an NK code, say 74 Hamming code. So it means that here we have the message bit 4, case 4. Then the parity bit R will be what? 7 minus 4, that's 3. Okay? And we know that this can literally correct 1 bit error and can detect 2 bit errors. Well, we'll also try to pull off, well, we'll provide details, okay, as we progress. So let's consider this as a general overview of what channel coding is all about. Then we have another code, the boss Kunduri Hopewell, that is boss Kunduri. ECH codes. Okay.
Sir, please, can you pronounce the bus Chanduri?
This bus Kunduri. That's Chauduri, bus Kunduri Hokwegem. Okay, that's the BCH code. Okay. Now, these codes are designed for multiple error correction. And they are also referred or known as very powerful cyclic error correcting codes. So cyclic codes are some special type of block codes, which we are also going to talk about shortly. So when we want to define the BCH codes, we not only specify the block length and the message bit, we also specify the error correcting capability, where we already know that N is the code word length, K is the message length or the message bit, and T is the number of errors that can be corrected. And we know that T is literally less than 2 to the M minus 1 over 2, where M is some positive integer greater than or equal to 3. Okay. So, well, the BCH codes, they are using your QR codes. We do a lot of QR code scanning and all of that. Even flash memories that use the NAND gates, Okay. So we also have the Rich-Solomon codes. Usually or commonly referred to as the ROS codes. Now, these codes are non-binary. So they are non-binary codes over the Galois fields or the finite fields. And they are used, now, these are not just used for correcting multiple bits error, they are used for correcting burst errors. So it means, for instance, if we have 101101110, and these consecutive bits are in error, then we say this is burst error, right? So it's different from having multiple bits literally, okay? So let's say this is in error and this is in error. So these are multiple bits that may not necessarily be burst errors, okay? So the BCH code will do very well here. But when we now want to consider consecutive bits that are in error, we want to deal with burst errors, then the Solomon code seems to be very robust for that. And we see that this also for an NK code can correct up to T to N minus K over 2 errors, okay? So given the parity N minus K. Now, these are just a few examples of the Hamming codes. We also have some other interesting cyclic codes, cyclic redundancy check codes, okay, that are very robust, in terms of various applications. We have those in the notes anyway. And then, but this also can be used for QR codes, your compact disc, your DVDs, and so many other applications. Also very interesting codes. Then another group of channel codes is the convolutional code. And we know that the convolutional codes are very interesting codes, largely because they use shift registers. Now, we already made mention of single bit error correction. multiple bit error correction, burst error bit correction. But when we now consider continuous data streams rather than blocks of code, then the convolutional code comes into play. So we can say that the work on continuous data streams rather than blocks of code. And here they use shift registers. For information encoding. So we have some interesting examples, in the lecture notes. So just speed through, and then you have enough time to look up what we have in the notes. Now, but the convolutional encoding is literally defined by a constraint length K and also a code rate R, which is a ratio of the message bits and the code word length. Now, if we say, for instance, we have a 213 convolutional code. So what we are trying to say here is that we have one bit or input bit. In this case, one input bit generates two output bits. This one input bit generates two output bits with a constraint length K, constraint length K being the same as 3. And this constraint length literally tells us the number of previous bits influencing output. Okay, so this is just telling us that we have this number of bits influencing the output. And the state diagram, like we have in our notes already, and the trellis diagram represent how previous bits influence encoding. Okay, so we'll also look up how the state diagram is used, how the trellis diagram is used. And for decoding the encoded convolutional codes, we use the maximum likelihood technique, which is the VTAB decoding. Okay. And the VTAB decoding algorithm is actually a dynamic programming technique for decoding convolutional codes. And the algorithm finds the most likely, that's why it's called maximum likelihood decoding scheme. It finds the most likely transmitted sequence using the trellis structure, okay? So it's going to trace quite a number of parts from relative to the decoded or the decoded bit sequence, and then compare the shortest possible part, and then maps with that, which makes the most likely bit sequence. So it's a very interesting, powerful decoding scheme. And the convolutional codes are used in GSM, CDMA. They're also using 4G LTE. They're using space, deep space communication, and so many other interesting applications as far as the existing wireless communication technology is concerned. Now, going forward, we now see that the block codes and convolutional codes built the foundation for channel coding schemes. And presently, in today's communication system, we now have variants of convolutional codes and block codes in place that now seem to be more robust, more reliable, and even more efficient than the traditional convolutional codes and turbo codes. And examples of such codes are the turbo codes, which modifies the convolutional codes, and the low density parity check codes, which literally modifies the block codes. And we see that in 5G technology and some other wireless communication technology, we now want to prefer the LDPC codes, or better still, the turbo codes. But the idea is that turbo codes concatenate two convolutional encoders and applies interleaver between them to generate the turbo code. And then it uses iterative decoding to decode. Very powerful, more robust than the convolutional codes. And the low density parity check codes literally relies on the parity check matrix, to which we are going to look up in this block code to also do same, and then also uses the iterative decoding, to decode the codes. These are very powerful codes. Now, now that we know that the block codes and convolutional codes forms the foundation or the basis for channel coding schemes, then let's just talk briefly about turbo codes before we move on. Turbo codes. Now, like I already said, the turbo codes literally improves on the performance of the convolutional codes by using an interleaver. Now, when we say an interleaver, it's just a code scrambler. Now, the turbo codes therefore combines two convolutional codes or convolutional encoders with interleavers. So when we mention interleavers, we are literally saying, well, this is code scrambler. So it means if, for instance, I feed into the encoder 10110, now the interleaver could scramble this code to now look something like 1010. How many ones do we have? 1, 1. So I have 1, 2, 3, 4, 1, 2 zeros. Yeah. So where we still have 4 ones, and we still have 2 zeros, right? So what the interleaver just did is to scramble the codes, okay? And this is to protect against burst errors. Okay, so that's what actually happens here. And for us to now, okay, let's look up how the turbo code works, because it literally concatenates two convolutional encoders to process the input, okay? And then once that is done, the interleaver scrambles the input bits and fits it into the next convolution encoder. And then for us to now decode, like I mentioned earlier, it uses the soft input, soft output decoders. So we'll call this CISO, all right? So, and this is done through iterative decoding. So in other words, the iteration will continue until there is convergence. So let's say, for instance, we want to transmit K bits. Let's say 101101. So what happens is that this input is fed into the first convolution encoder. And then the first convolution encoder takes in this input as it is. And then it will now feed it into the interleaver, which will now scramble this code to reach something like 110011. How many ones do we have? 1, 2, 3, 4. 1, 2, 3, 4. Yeah, I think we have the same thing now. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Into something like this. And then this interleaved output is now fed into the second convolution encoder, this convolution encoder 1, into the second convolution encoder. Okay, and while this is being done, we have the parity bits added, and then the output of this is literally a systematic code. And we already know what the systematic code is. I'm sure we mentioned that in our introductory class, where the message bits and K rather are distinctly separated from the parity check bits. Okay. Now, this is how the turbo code encoding operates. And then we also now decode this. So it means that the single input, single output decoder will now take in this systematic code from the second convolution encoder to estimate the original data. Okay, so the interleaved version will now be fed into a second decoder because we performed 2 encoding, so we're going to also perform two levels of decoding. Then afterwards, we now do the log likelihood ratio computing, where we are able to now compute the likelihood of each bit, either being a 0 or a 1. Then there's the extrinsic information exchange, where the first decoder sends reliability information to the second decoder and vice versa. And this process will continue in an iterative process till the original bit is decided upon. So that's why we call it an iterative process. Okay. So the idea of sending reliability information between the decoder 1 and the decoder 2, you know, till we now derive our originally transmitted bit sequence, you know, is which goes through a number of sequences, makes this decoding scheme an iterative system. Okay, so technically for decoding, we have the decoder 1, then from which the interleaved output is rearranged. So after rearranging the interleaved output, then we'll come back to our decoder 2, and then this process is done until we arrive at the output. Okay, so we have algorithms running this, and you could also play with such codes. And then, like I mentioned earlier, the block codes, the convolutional codes form the foundation for what we do. Then we have the low density parity check LDPC codes. Okay. And this follows directly from the linear block codes, okay? But what happens here is that they use sparse parity check matrix, okay? So that's H. And this is the same parity check matrix we use for syndrome decoding, okay? And this also uses a graph-based decoding system, which you call the Tanner graph, okay? So it's equally a very interesting, powerful coding scheme. And here we also adopt the iterative belief propagation decoding. So how do we generate the LDPC codes? So for us to be able to generate the LDPC codes, now you observe that in all of the channel coding systems, we have the channel encoding process and also the channel decoding process. The same way we have the source encoding process and the source decoding process. So for us to be able to encode the low density parity check codes, we literally represent these LDPC codes using the parity check matrix and the generator matrix, okay? So, well, when we look up the block codes, then we get this right again. So we have the parity check matrix, and also we have the generator matrix. Now, what's the generator matrix like? The word generator, this is what we use to generate the code words, okay? So we are going to see how it is done, how we use this to generate the code words. And now, if we use this to generate the code words, the generator matrix, then it means that we will also use the parity matrix to decode the code word. And that process is called syndrome decoding, right? It's a syndrome. So it means that the generator matrix and the parity check matrix are derived or designed from each other. Okay, so, okay, well, I'll come to that. So that the parity bits will have to be common for both the generator matrix and the parity check matrix. And here we say that the parity check matrix is a low density binary matrix, largely because most of the elements will be 0 or are 0, okay? And it defines the parity constraint on the code bits. And for the parity check matrix, each row, this is, let's say, row 1 up to row n, represents the parity check equation, okay? So this represents the parity check equations. And since both the parity check matrix and the generator matrix are derived from the same parity matrix, then, or parity bits, then the product of the generator matrix and the transpose, or let's say the product of the parity check matrix and the transpose of the generator matrix, which is also the same as the product of the generator matrix and the transpose of the parity check matrix, must be the same as 0. Largely because the parity check matrix is designed in such a way that we have the parity bit and the identity matrix, while the generator matrix will not be such that we have the identity matrix and the transpose of the parity matrix. So it means that the parity matrix P must have been defined, okay, where we have this as a matrix. So with this parity matrix, which is common to the parity check and the generator matrix, we'll now design that. So since these two are common, so this is literally the transpose of this. So with the generator matrix, we are able to design the code word. And as such, with the parity check matrix, we are able to decode the same set of code words. Okay? And if this condition is satisfied by the generator matrix, then it means that the code words are generated by literally multiplying the message sequence by the generator matrix. So this is how we get the code words. So this is the message bit. This message bit multiplied by the generator matrix will now give us the distinct code words, the possible code words that can be transmitted over the channel based on this algorithm. So it means that the parity check matrix and the generator matrix have an idea what the possible code words could be. Does that make sense? Does that make any meaning or any sense?
Yes, sir. Yes, sir.
Okay. So now, if that's that, then how do we perform the low density parity check code decoding? So how do we perform decoding? Like I mentioned, for us to be able to decode the LDPC codes, we use the belief propagation algorithm, which is also known as message passing, right? So I call it message passing or belief propagation. And then we perform what we call graph representation. Call this the Tanner graph. Okay. So in other words, the LDPC codes are represented as what they call it, the bipartite graph. That is, we have the variable nodes, we have the check nodes, and then we have the edge connection. So how do we do this? Now, the variable nodes give us the code word bits, and then the check nodes give us the parity check constraints. Parity check. Constraints. So let's take, for instance, we have a simple 6-3 LDPC code. Let's say we have 6-3 LDPC code. So this is N, this is K, okay? And here we have the parity check matrix, 101, for instance, 110, 0, 1, 1. And then we know that we have the identity matrix, 1, 0, 0, 1. So from this, we already know that based on the formulation that the parity check matrix is the parity and the identity matrix, whereby the generator matrix for this will be the identity matrix and the transpose. So if we bring out the parity here, that's 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, and 0, 1, 1, 0, 1, 1. Then the transpose of this, so the row becomes the column, that'll be 1, 1, 0, that's this, first row. Then the second row, 0, 1, 1, 0, 1, 1, and then the third row, 1, 0, 1, 1, 0, 1. So the generator matrix here will now be the same, where we have the identity matrix, 1, 0, 0, 0, 0, 1, 0, 0, 1, and then we now have the transpose of the parity matrix, 1, 1, 0, 0, 1, 1, and 1, 0, 1. So this is what will be used to generate the code words, right? This matrix. Why this parity check matrix will be used for decoding. But now, now that we are talking about decoding, so we have to deal with this, right? So this is I just wanted to show this briefly so that we know. So we are not interested in this right now. We've done our code generation and using the relevant algorithms, and then that is it. So how do we develop the Tanner graph here? Okay, because we have to perform graph representation for our decoding. So, and we already know we have the variable codes, the check nodes, and then the edge. We have the edges, we have to connect both the variable nodes and the check nodes. So in this case, each row 1, row 2, and row 3 forms the parity check equation, as we said earlier. So how do we identify these nodes? So it means that each of these, which is V1, V2, V3, V4, V5, V6, forms the code word length, right? So, well, we've not done the code word generation. So, and now, for us to be able to tell the variable nodes, then we should be able to pull out each of these parity check equations for which we have 1, 1, 0, 1, 0, 0. So it means that V3 is turned off, V5 is turned off, V6 is turned off. So we only have V1, V2, V4 turned on for row 1. So for us to be able to get the check nodes, it means that we are going to be having 3 check nodes, right? C1, C2, C3, which represents the parity check equations, right? So for row 1, we are now going to have C1, which is the same as 1, 1, 0, 1, 0, 0. And we know V1, V2, and V4 are turned on, right? So it means C1 will be the same as V1, V2, V4. Is that clear?
Yes, sir.
Yes, sir.
So it means that C2 will be the same as V2, V3, V5, V2, V3, V5. And C3 will be the same as V1, V3, V6. Now, it means that in this case, we have 3 parity check equations. And then we can design the Tanner graph from this, since we have C1, C2, C3, mapping to V1, V2, V3, V4, V5, V6. So this graph is now going to look something like this. So we can change the color. So C1 will connect to the edges of C1 will connect to V1, V2, and V4. While for C2, it will connect to V2, V3, and V5. While C3 will connect to V1, V3, and V6. Now, if you've been reviewing some literature, you know, where you had to look up some of the LDPC codes, so you must have seen something like this, right? Which they refer to as the Tanner graph. Okay, and this literally represents the mapping of the check bits and the nodes, right? So that's about that. So we've been able to connect the check nodes and the variable nodes together. And once this is done, having established this, then we can now perform what we call the decoding using the belief propagation algorithm. So in this case, we want to perform the initialization such that each variable node, we already established the mapping. So each variable node will now receive the log likelihood ratio of received bits. Okay. And then afterwards, we want to check for node processing. And for us to do that, the check nodes will now calculate the parity constraints. Then once the parity constraints are calculated, the variable nodes will now update. The variable node or nodes will now update their estimates based on the check nodes. Okay, and we already have the equations that forms this process, and then the process will continue to repeat until we achieve the parity check times the code word being the same as 0, which is a syndrome. This is a syndrome decoding syndrome. And once this is the same as 0, it means there is no error in it. So that's why it's an iterative process. Okay, and then the hard decision is made. So after sufficient iteration, then once the syndrome reduces to 0, then we say that is the transmitted code word. That's how interesting the LDPC code performs. So literally speaking, I'll say that we've concluded our discussion on channel coding. Okay, so any question? Any question, please?
Yeah. Good morning, sir, Doctor.
Very good morning.
Yeah, good morning, sir. Yes, sir. Thank you for this class because I think this class actually reminds me of I don't even know how I actually managed to write my undergraduate project because my project was also based on error transmission, detecting error in image transmission through using convolutional and block codes.
Okay.
So yeah, that was the undergraduate. So I just kept remembering those old goodies. So but during that time, I was being asked, I think you were asking for some kind of coding, like did I run any simulation? That was during project events. Is there a place of we running a kind of a simulations? If you're going to bring in the application aspect now, maybe you want to detect error in image transmission. So what's the technical know-how, sir?
Perfect. So we have to do coding. Now, just like I mentioned, you see that bulk of what we have now done requires programming. Okay, it requires programming. And you want to program after you have developed an algorithm. And this algorithm is what will run in your encoder and decoder. Okay, so that's about the practical implementation. When we now have to look at how these things work. So what do I do now? Probably we play with one simple illustration to show how this works. Will that make sense?
Yeah, I was even about to ask that.
Yes, sir.
Yes, sir. Well, I was even about to ask that. So before we proceed, sir, that means for us to simulate or encode, that means we have to have generated a particular code before we proceed for the simulation. Is that right, sir?
Can you explain what you mean?
like it was like referring back to the LDP, referring back to the LDPC. So we actually generated a parity, I mean a transpose, and from there you said we're going to have a formula from the parity check. So I mean, if from that parity check, is it the formula we generated that will now be used to uh develop our codes?
The formula you generated, are you really going to come up with a formula? I don't think so. Because when you say formula, I think it brings me back to our rigorous mathematics, right? Where everything is all about formulas, isn't it? Right?
Yeah,
And
actually.
and if you are not coming up with a mathematical model, you have not done anything, right?
Yeah.
But in this case, you are literally implementing your code using some kind of logic.
Okay.
You are using logic. Mind you, what we are dealing with are zeros and
one.
ones. Okay?
Okay. Yeah.
And then we said, from now you're bringing me back to basis. Okay, that's what I try to avoid. I just went off to talk about the channel coding schemes, believing that you must have looked through our previous lecture notes, right? On error correcting codes. Now, when we come back to basis, we say the foundational channel codes are block codes and convolutional codes.
Okay.
And convolutional codes. Okay? And now, when we say block codes, it means that they do not have memory. Now, these ones, convolutional codes, they use shift registers. So it means that they can hold on to a bit till it is moved to another register. So it means they have memory. Why this is memoryless, right? Now, if the block code encoder is memoryless and the convolutional code encoder have memory based on the fact that it uses shift register. Now let us go back to our digital communication. How do we implement such systems using hardwares? We use combinational circuits, right?
Yeah.
Where we don't have memory. Now, for the shift, where we now have shift registers, we now have to use sequential logic, right?
Okay.
Now, is this making sense in terms of application? You want to apply. Now you've designed this code. Now I want to implement this code. So it means that we have logic. This is now, and the addition we perform here is modulo 2 addition. So probably when you look up the notes, you appreciate this point. Now we use modulo 2 addition, and for modulo 2 addition, which of the gates performs modulo 2 addition? Can you remember that? Just going back to fundamentals now. Which of the gates performs modulo 2 addition, if you can remember? Yeah, we have our good friend here who actually did something on coding in undergraduate days. Can you please unmute? Let's hear your voice again.
Sir, yes, I'm with you, sir.
Yeah, that's Mr. Taiwo, right?
Yes, sir.
Yeah.
Yes, sir.
So you devise or you design the code in your undergraduate days, right? For error correction and detection.
Yes, I did.
Okay, fine.
I
How
actually
did
it was
you
on.
now just 1 minute? How did you achieve your results? Did you run simulation using some program?
What I did was I ought to have used MATLAB then to do that. But what I did was just to do I wrote it, I wrote it out and now added it to the back of my this thing. So I didn't do the simulation on ground that particular day because of the time frame and the situation on ground. So I just generated something and pasted it.
It's okay. It's okay. It's okay. And you must have had that in your institution, right? Many years ago, before coming to the University of Lagos, isn't it?
Yes, sir.
Beautiful.
Yes, sir. Almost 5 years.
Oh, almost 5 years. That's quite some time. It's a long time. Now, the idea is this. If I want to perform my modulo 2 addition, which you will say 1 modulo 2 addition 1 is equal to what? 0, right? Isn't it? So I say
Yes, sir.
1 modulo 2 addition of 0 is equal to 1.
1.
Now, what I'm actually using is an exclusive OR gate to perform this operation, where this is AB, and then this is A exclusive OR B. Okay, so it means that if I have to implement the hardware that will perform this operation, then I'll have to come up with my exclusive OR gate, which is a combinational circuit, right? Does that make sense? Hello? Yeah.
Yes, sir.
Now, let's come down from that high horse in terms of practical implementation. We now know that if we have to implement the block codes, we are going to be using all of those AND gates or OR gates, exclusive OR gates, even NAND gates, right? NOR gates, exclusive NOR gates, right? Even the NOT gates, the buffer. Now, all of these will now have to connect in a manner that will operate on our bits and generate them, because now this is where integrated circuits come in. Hello? Now,
Yes, sir.
so we are not going into,
Yes, I will.
so we are not going into electronics, okay? So we are now stepping down to digital electronics. So if I'm saying, if I'm going to have a 1 or 0, so what's really happening in all of those, your processors, okay? So when we say machine language, we are used to implementing all of those codes and blah, blah. Now, for me to be able to draft or run my program based on all of these combinational circuits put together and all of that, even my flip-flop. So it means that I'll have to do what we call hardware programming. So we don't only program software, right? And I'm sure you know what this is, right? Hardware programming. So now, which of the programming languages comes to mind when we say hardware programming?
We have the C++.
No, that's not
C.
for hardware. So we have the VHDL.
Oh, okay.
Yeah, we have VHDL. So we could also do Verilog. Okay, or Verilog system. Okay. Now, if you look up my updated notes on digital computer technology, there we try to play with Verilog, okay, in terms of programming hardwares. So there, I think we use the model scene there. So you see how we are able to run the VHDL codes in terms of playing with our hardware implementation. So this now brings us to our coding. So if I now have to implement my convolutional codes, then it means that I have to now introduce alongside these combinational circuits, the likes of my AND gates, NOR gates, NAND gates, or whichever, I will now have to introduce flip-flops, right? So once I introduce flip-flop into my design, then it means I can literally latch on a particular bit and hold on to it till I get the next trigger, isn't it? Hello? Are we still together?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes,
Yeah.
sir.
So Mr. Taiwo, are we running on the same page now when it
Yeah,
comes
yes,
to
sir. Yes, sir.
when it comes to implementing this code? So in as much as we try to play with all of the zeros and ones and all of that, for us to now be able to implement this code in practical systems, we now have to come back to digital communication, where we now have to play with all of those combinational and sequential logic. So I know if I have to implement my low density parity check codes, it builds on the block codes. So I'm going to be relying on my combinational circuit, but this time I'm going to be drafting a program. So we could literally implement this using VHDL, where we now have a loop that where we'll be able to program for our where we'll be able to iterate, because there should be that iteration. For us to have iteration, then we have to define some loops, right? Like in your programming, like you're doing your high-ended programming whatsoever. So the problem is engineers now want to become scientists, right? So you want to concentrate more on your software development, C++, and all of those regular programming languages. But there's one aspect that is critical to us as far as the electrical, electronics, and the computing engineering phase is concerned, and that is programming hardwares. And now you see that a single chip integrated circuit device could contain billions of transistors. And you know that your regular AND gate is just a combination of some transistors, right? You still remember some of these things? I know it's been a long time for most of you. Hello?
Yes, sir.
Okay. Now, is it still making sense? Because we are literally coming back to basics. Okay, going back to some of those fundamentals. Can we still remember them?
Yes, sir. Yes, sir.
Okay. So we now see that our regular circuits, the AND gates, what's it called now? And OR gates and all of that, they are simply transistor devices put together. Okay. So, and you now see that for us to be able to appreciate this, we still have to come back to the fundamentals. So we are literally coming back to electronics, and then we now have to come back to very large scale integration. And then, but good enough, we now have, platforms where we could just emulate or simulate these ideas. So you don't have to begin to build from the scratch. Okay. Does that make sense, please?
Yes, sir. It does.
So I think with that, we can now begin to move on and just so don't forget, it all comes back to your bipolar junction transistors and feed effect transistors. You recall your MOSFETs, right? So And with those, you are able to implement most of those so it's just that, well, all of these gate things just make us lazy. Can we say they make us lazy? Can we? Hello?
Not actually, sir.
Not actually. At times they make us forget where we are coming from.
Yeah, exactly.
So at some point, you want to go back to some of those basics to say, well, my AND gate, how does the transistor, what was the transistor equivalent for my AND gate, for my OR gate, for my NAND gate? Now that is why we say that that single chip you have and you call it integrated circuit literally connects billions of transistor devices, okay? Billions of these together to perform what we call switching, okay? So they are all interconnected, and each of the modules and block probably have a NAND gate, some have the NOR gate, some have the NAND gates, and all of that, all connected together, okay? And with that, we are able to perform switching. And step up a bit, then we are able to also integrate our flip-flop models, which is still a combination of, now your flip-flops is still a combination of your combinational circuits, only that we are able to use it to, we're able to maintain a certain state, depending on the type, is it JK, SRO, T flip-flop, depending on the type of flip-flop and all of that. So probably if you want to revise that concept, you want to look up the lecture notes on digital computer technology, where we played with all of those jargons and all of that. And then that will now bring us back to the practical implementation of some of these coding schemes. Is that okay?
Yes, sir.
Okay. So, Mr. Taiwo, have we addressed your concern?
Yes, sir. Yes, sir. Thank you, sir.
So you now
Very well.
now you don't have to learn C++. You just have to learn either VHDL or Verilog, right?
Yes, sir. I remember that VHDL, but during my time, I had to find someone to assist me. So he did that and sent me the result. That was what I attached. Remember, I think it was is it Verilog or Verilog?
Verilog. Okay,
Verilog. Yes,
you played with Verilog then to implement.
Yeah, he played with it and sent me the thing.
Okay. So I wish your supervisor did not let you graduate then. So probably you would have done it yourself. All right. And then you would have said, well, this man is mean, but he would have done the best thing anyway. That's fine.
Yes, sir.
Well, it's good enough. We are now here, and I think you may not be able to escape it again. So you now have to go back. And all thanks to technology, you can now learn these things within the comfort of your home, right? It's just to, just to activate your data, and then depending on what you ask, you're going to get that from the pool of knowledge we have all out there. So, okay. So, okay, now I think we've been able to establish, how to implement these things in practical terms. So we are still not veering off. So we are not just basing our idea about mere analysis. Okay, so, and at times it becomes very difficult to step down from all of those differential equations to some zeros and ones. Okay, so think it's more like coming down from the high horse and trying to see things the way from the microscopic view, okay, which may not really make sense interpretively, but except we are not able to encode the interpretation we want from it. Okay. Okay. Now, we've literally made mention of quite a number of things, and there are some things I may not have mentioned when we have to play with block codes. So I think I'll just come back. So now we already know where we are at in terms of technology, and then we can literally walk back to the basics now. Hope that will be fine. Would that be fine?
Yes, sir.
Okay.
Yes, sir.
So it means for those of you that are that will be conducting your class assignments, the channel codes or coding will be one good place. So you now have a long pool. So we have the block codes. You could play with the Hamming codes, the with Solomon codes, the even Gole codes, which I didn't mention, the Bosco-Hunduri, Hopogram codes. Now you could apply them, okay? So probably you want to optimize these codes. You could also play with the convolutional codes. Probably you want to address some challenges in GSM technology, in your third generation technology, WCDMA, and even your fourth generation technology, your long-term evolution technology, LTE. Okay, so your convolutional codes equally apply. And alongside, we now have the turbo codes that also apply, you know, even in your LTE, your 5G, and all of that. Probably you want to look up how to optimize the turbo codes. Then you may want to go a notch higher and say, well, let me stick with my block codes and then let's look up the LDPC codes. How do we optimize them? Now, when you search in the literature, you're going to see a pool of contributions from researchers where they have been able to experiment in terms of, you know, optimizing these codes and all of that. Okay, so hopefully before the month runs out, you should be turning in your assignments. So you want to concentrate in this area. So you have some interesting codes to play with now. Okay. And for us to just build the basis, so we now want to look up the linear block codes. Where did it all begin? Now, we already mentioned that the linear block codes are described in terms of the generator matrix, and the parity check matrix, right? So while we use the generator matrix for encoding, we use the parity check matrix for decoding. Okay. And one common word we use here is syndrome, called the syndrome decoding. Okay. So now that we mentioned the linear block codes in terms of your research, you can begin to look up, think in terms of the block codes we've talked about, then the cyclic codes. Then you can also think in terms of your low density parity check code. Okay, can scale down, you know. And funny enough, whatsoever you end up doing here, if you're one of my project students, you could just improve on it, and that becomes your main research activity. And good, and we are good to go. Okay, and now there's one concept I would love us to, some concepts, you know, terminologies I would love us to bear in mind, like the minimum distance requirement. So when we talk about minimum distance, we literally mean that should we have some codes? The minimum distance of block codes determines the random error detection and random error correction capabilities of that code. So how do we measure this distance? So we start the minimum distance or Hamming distance or the shortest Hamming distance between different code words in the code literally tells us the smallest weight of the non-zero codes in the code. Okay, so we now note that the Hamming distance, when we say Hamming distance, the Hamming weight, so the Hamming distance between two code words. So let's assume I have one code word 1011, and then I have another code word 1000. So the Hamming distance between these two code words is the number of places in which the code words differ. So we can literally say it is the weight of their modulo 2 addition. And when we look at this, we see that they only differ in 2-bit position. So this has 1, 2, 3, and this has 1 bit. So the Hamming distance between these two is 2. But we now say it is the weight of the modulo 2. So if we take the modulo 2 addition of these 2 bits, so this plus this is 1, 1 plus 0, 1, 0 plus 0, 0, 1 plus 1 is 0. So we have 2 bits here, and the Hamming weight is the number of non-zero elements. So the Hamming weight here is the same as 2. So the Hamming distance literally is the same as the weight of the modulo 2 addition of these two different code words. Does that make any sense for now? Is this clear? Hello? I hope.
Please, can
Please,
you
can you
recap?
come again on that
Can you
last?
recap? Yeah.
Okay. Now we have Hamming weight. Then we have Hamming distance. So we gave two code words. We have 1011, and we also have another code word 1000. So what is the weight? What is the Hamming weight of this code? Hamming weight. So the Hamming weight is the number of non-zero elements. Number of non-zero elements gives us the Hamming weight. So the Hamming weight here is 1 to 3. So this have a weight of 3, and this have a weight of 1, because this, the non-zero element here is just 1, right? And the non-zero element here is 3. Is that clear for the Hamming weight?
Yes, sir.
And now we are saying that the Hamming distance is the number of elements in which they differ. So when we now want to take the Hamming distance between this code word and this code word, we now say, well, the number of elements in which they differ is the weight, is the distance. And how do we estimate that? So you see that we begin to look at these two. Say, okay, and where do they differ? Okay, this 1, 1 is common, 0, 0 is common. Okay, they differ in these two positions. 1, 0, 1, 0. So now that's the Hamming distance. But now you want to put up a program to do this using your hardware description language, for instance, either your Verilog or your VHDL. So what are we going to tell this to do? So we are not saying that the Hamming distance between two code words is the same as the weight, or better still, the Hamming weight of their modulo 2 addition. And recall we played with all of this modulo 2 addition, multiplication when we talked about the Galois field. So don't forget the binary vector space mathematics is what plays here. That's what we are literally dealing with as far as coding is concerned, right? And if I now have to tell my program to estimate the Hamming distance between these two code words, it means that it will have to take the two code words and perform the modulo 2 addition. And if I should do that in this case, the modulo 2 addition, so this is going to give me 1, this is going to give me 1, this is going to give me 0, this is going to give me 0. So the weight of this addition is 2, and that is the Hamming distance. Does that make sense?
Yes, sir.
And now we are saying that the minimum Hamming distance or the smallest Hamming distance between different code words in a code determines the error control capability of that code. So this is very, very, very important because it is the smallest weight of the non-zero code word in the code. And that gives us the idea of the error detection and error capability of the code when it comes to designing the code. Is that clear? Is that clear, please?
Yes, sir. He said that will lead us to the error determine or error. Say something about
the error detection
detection. Okay.
and error correction capability of the code is determined by the minimum Hamming distance.
Okay, sir.
I know when I have to say a lot of things and not write it down, I understand. Okay. So we've made mention of so many things, and like we also mentioned earlier, a sufficient condition that must be satisfied for us to have a generator matrix and a parity check matrix is that the multiplication of the parity check matrix and the transpose of the generator matrix, or the multiplication of the generator matrix and the transpose of the parity check matrix must be the same as 0. And we also mentioned that the generator matrix, which is used to generate the codes, is such that the code word is the same as the product of the message bit and the generator matrix. Okay? And when it comes to decoding, then for us to be able to decode, then the code word multiplied by the transpose of the parity check matrix, which is the same as the message bit multiplied by the generator matrix multiplied by the transpose of the parity check matrix, must be equal to 0 for error-free transmission. So this is syndrome decoding. So if this condition is not satisfied, it means there is an error. So technically, you have literally instructed your logic gate devices to manipulate these symbols. And you now say, well, when we receive this, we already know the possible code words we are going to receive. Please, this is the parity check matrix. Take the inverse of this, multiply by that, and whatsoever we get, if it's not the same as 0, then you know there is an error. Then we now tell our program, once you discover that error, you now want to map that error with what we have in the parity check matrix to tell the location of that error, and then take that as take that bit position, flip that bit position for the received code word, and then test again to see if the syndrome will be 0. If the syndrome is 0, then it means that is the correct code word, or that is the originally transmitted code word. Then feed it out as the output. Okay, so we are literally, this is a program running here. And we know that we know so many ways we could correct for errors by using parity check bits, either even or odd parity, repetition codes, and all of that. So I don't want to go into all of those things. Then we also have cyclic codes. Okay, so these are a subclass of the regular linear block codes. So we have cyclic codes. Okay, so and the cyclic codes, like I mentioned, forms a subclass of the linear block codes. And a code is therefore said to be cyclic if it literally satisfies two conditions. That is linearity property and also cyclic property. So for linearity property, it means that the sum of any two code word is another code word. So we played with that in the Galois field, right? And which led to the irreducible polynomial, if you remember. So it means that if we add up two possible code words, it must give us a code word in that subset. It means that it is linear. So when we say linear block codes, the linearity of the codes is that the sum of any two code words in a code will also give us a code word. And then for the cyclic property, any cyclic shift of a code word in the code is also a code word. Okay? So should there be a shift, then we are also, that shift is going to also give us a code word. So a cyclic code is therefore a lateral or cyclic shift of one another. And this applies in OFDM schemes and all of that. Okay, and we have some interesting advantages for the cyclic codes, and those you can look up the previous note. Okay, so the error correction and the coding methods of the cyclic codes are simpler. The encoders and decoders for cyclic codes are also simpler compared to the non-cyclic codes. We have quite a number of them, you know, they have easy syndrome and all of that. Okay, only that the complexity in terms of their circuit or combinational logic circuit design is a little high. Okay, then there are a number of cyclic redundancy check codes, and you know, we've already mentioned or talked about the BCH codes and their properties, the Solomon codes, and all of that. So, and we also have some interesting examples in the note, which I don't think I would love to play with, but let's just consider one interesting example. One interesting example. So let's say we are given a 7-4 cyclic code. And here we are given a generator polynomial 1 plus x cubed. So recall the Galois fields. You know, we played with the Galois fields and then went on to introduce information theory, the concepts of information theory, and then moved into source coding, and now we just arrived at channel coding. So once we're done with channel coding, then we'll move into what happens in the channel. I think then we'll be done, okay? So we have this, and now we want to determine the code word if the data word is 1011. So here, let's define the instances. We have this, and then say we want to determine data word. So the first part here is data word or message bit is given as 1011. So what is the code word? We don't know. And the second instance is that the code word is given as 1100101, and then what is the data word? Okay. And we've been given the generator polynomial for the 7-4 code, cyclic code. This is a block code. I will know for 7-4, it means N is 7 and K is 4. So it means the parity bit here will be 3, isn't it?
Yes, sir.
Okay, good. Now, we have the data word in this instance. So if data word D is the same as 1011, so we can literally pull the polynomial in this. So it means D of X will be the same as, so if this is S0, S1, if this is S0, S1, S2, S to the 3, or S cube. So what do we have? S, anything to the power of naught is 1, right? So S0 will still give us 1 plus, now, X is turned off here. So we have X squared plus X cubed. Okay, is that clear? Hello?
Yes, sir.
Now,
Yes, I'm with you.
okay. And don't forget that this, they said this is the generator polynomial. Okay, so we can literally call this G of X. Okay, now with this, we can generate our generator matrix. Now that we have this, we already know that the code word, C is the same as the message bit times the generator matrix. And this data word is literally our M of X. Then we have G of X. So we can evaluate the polynomial, a code word or the code word polynomial to be the same as D of X, G of X. Right?
Yes, sir.
And then this now will be the same as 1 plus X squared plus X cubed times the generator matrix, which is 1 plus X plus X cubed, right?
X cube.
Yeah.
X cube.
Sorry, sir. I didn't know how you got that D of X.
Okay, we got it from the data word. This is the data word, which is given, and we have to evaluate the code word, right? So,
Yes, sir.
yeah, so from the data word, we call your Galois fields. We can literally convert this to the polynomial. So where this is equivalent to X0, this is equivalent to X1. So the power of the variable increases. This will be X to the power of 2. This will be X to the power of 3. Now, this now can be rewritten as X0 times 1 plus X to the power of 1 times 0 plus X squared times 1 plus X cubed times 1, right? So X, anything to the power of 0 is 1. So this is 1 times 1, right? Plus anything times 0 is 0. So this is plus 0. X squared times 1, X squared. Plus X cubed times 1, X cubed. So this will now be 1 plus 0 plus X squared plus X cubed. So this will be 1 plus X squared plus X cubed. So that's how we got this.
Thank you very much. I understand now.
Okay, you're welcome. Now that we have this, so we can now expand this times this, that is 1 plus X cubed plus x squared times x cubed, s squared times s cubed, x to the power 5, plus s cubed times 1, x cubed, plus x to the power 5, plus x to the power of 6. And then we can now collect all the like terms. So we have 1 plus x.
So there's one that's supposed to be x to the power of 4.
Yeah, x to the power of 4. I missed it out.
Yeah, that's the one for 5 here. Yeah.
Yeah, x to the power of 4. Yeah, thank you for that. Then all of the x squared, how many of them is just 1 plus x squared? Now, all of the s cubed, we have 3 of it, x cubed plus x cubed plus x cubed, right? Then s to the power of 5 is 1, right? So we have 1 s to the power of 4 plus x to the power of 4, then plus x to the power of 5 plus x to the power of 6. Now, we can now rewrite this again. So x cubed plus s cubed plus s cubed is going to give us s cubed, right?
Yeah.
Modulo 2 addition.
Yes, sir.
1 plus 1 is 0 plus 1 is
0 plus
1.
1. Yes.
So this is now going to reduce. Okay, so let's pull this up. So let's
So, guys, I need this email. There's email from is it MTN
Okay.
that they block Fresh Wireless.
so let's pull this up.
Okay.
Fresh Wireless.
So let's pull this up.
1 second, sir.
Okay. Okay, go ahead. You need
So I
any,
think the x cubed, they are supposed to be 4, actually.
are they up to 4? Let's look at it again. This time this
It's 3, sir.
is 3. This would be s cubed and this would be s to the 5. Then it's 3. It's going to be 1, 2, 3. So you want to expand it again. This is the first bracket. This is the second bracket. This is the third bracket. When this multiplies everything, then x squared multiplies everything, x cubed multiplies everything. Is that okay?
Yeah, it's okay.
Yes, sir, it is.
Okay, so now it means that this is now going to give us 1 plus x squared plus x cubed plus s to the power of 4 plus s to the power of 5 plus s to the power of 6. So we can now return this. So this is x naught, x to the power of 1. So they are all complete. So we can now convert back to binary position. So our code word will be 1, 1, 1, 1, 1, 1, 1. So this is our code word. So it means that given this transmitted data and having the generator matrix, once we multiply the transmitted data to the generator matrix, we are going to get a specific code word.
Sir,
Go ahead, please.
sorry, question. I was not like how we reduced the 3 s cubed to just only 1.
How what?
The s cubed. Yeah, I mean it's not only 1. It appeared only once here.
Yeah.
What's the reason behind
Okay.
it?
So that's now I would love you to revise our note on Galois fields or finite fields. So now we have x cubed plus x cubed plus x cubed. Now don't forget, since we are in the binary vector space, our addition is not literal addition, it's modulo 2 addition, right? And we can achieve this using the exclusive OR logic gate. So this means that if we take x cubed out, so it means we have 1 plus 1 plus 1, right?
Yes.
Yeah. So from modulo 2 addition, 1 plus 1 is supposed to give us 2. But since we are in the binary vector space of 2, then what we now do is that Okay, let me change this. Let me designate this properly. So the vector space is 2, right? That's our vector space. So let me leave this as n. So what we do is that we cannot receive 2 in binary. So the maximum now is 2. So what we do, we divide by the base. So that's going to give us 1, remainder 0. So we discard this and the remainder becomes our answer. So it becomes 0 plus 1, right? Is that clear?
Yes, sir.
So 0 plus 1 is now equal to 1. And recall that this is all in this bracket x cubed. So it now means 1 times x cubed is going to give us 1. So that's how this reduced to 1x cubed. So let's assume we had just s cubed plus s cubed. So it would have reduced to 0. So it will now be 0 times s cubed. So this s cubed plus s cubed will disappear. Does that make sense?
Yes, sir, it does.
Okay. Now, the next thing is to evaluate the code, the data word given the code word. Okay? So we now have to follow a similar approach. So let us see how we do that. So we have been given the code word C to be 1100101. And now we have the generator matrix to be the same as 1 plus x cubed, right? So we can now convert this again. So recall this is x naught, s to the 1, x squared, x cubed, s to the power 4, s to the power 5, x to the power 6, right? So it means that the code word, now s to the power of 2 and 3 and 5 will knock off to 0, right? So we have x naught plus x to the power of 1. So this knocks off to 0, 0, then x to the power of 4. S to the power of 5 knocks off to 0 plus s to the power of 6. So it means our code word is the same as 1 plus x to the power of 4 plus x to the power of 6. Is that clear?
Yes, sir. Yes, sir.
Okay. Now, if that is clear, we know that the code word, the polynomial, is the same as the data word polynomial times the generator matrix polynomial. So for us to now evaluate the data word, or D, in binary, so it means that the data word will be the same as the code word polynomial divided by the generator polynomial. So we already know that the code word polynomial is 1 plus x to the 4 plus x to 6. And then we divide that by the generator polynomial, which is 1 plus x cubed. So we can perform our long division here. 1 plus x to the power of 4 plus x to the power of 6 divided by 1 plus x cubed. Okay, and we can now perform this operation. Or technically, we want to rearrange from the highest power to the lowest power, and then we can just do that as for our long division. So that will give us x to the power of 6. Now, I want to make something easier here. Now, plus x to the power of 5, I want to leave all of the bit positions, is 0. Then we have x to the power of 4 plus s to the power of 3 is 0, s to the power of 2 is 0, plus x plus 1. Let's leave all the spaces. So here we have x cubed plus x plus 1. Running this division. So let us go through this. So x cubed can go into x to the power of 6 x cubed times. Right? So that we have x cubed times x cubed would be x to the power of 6. Now, x cubed times x will be x to the power of 4, right? So that can come here, x to the power of 4. Now, x cubed times 1 will be x cubed. Now, we don't have x cubed here, so we can say x plus x cubed. So we can add up, right? Modulo 2 addition. So this is 1. This is x plus. Now, x cubed 2 can come in here, x cubed. So plus 0, 0, right? So x cubed can go into x cubed one time. So we now have plus 1. So x cubed times x cubed will be x cubed. 1 times x cubed rather is x cubed. 1 times x is plus x. 1 times 1 is 1. So here we have no remainder. So it's all 0, all right? So it means that the data word is the same as x cubed plus 1. Okay? So it means that if we now open this up, this x cubed plus x squared plus x plus 1. So it means this is 1, this is 0, this is 0, this is 1. So our data word is 1001. Is that clear? Hello?
Hello, sir.
It's clear. It's clear to me.
Yeah, okay, go ahead.
Yes, sir.
Okay.
The data code that we have, which is x cubed plus 1.
Mhm.
After writing it down, we have to arrange it so that 1 will start before the x cube, or we can leave it like that.
Well, we are literally working with the highest power. So it means there are some other bit positions in this sequence. So we know that 1 is x naught, and this is x cubed. So it means we have some bit positions that are not active, the likes of x squared and x to the power of 1. So we have to show their position, although it is 0.
Okay, sir.
Hello, sir.
Now go ahead, please.
Yes, sir. Please, I think what the question is,
Go ahead.
since our final answer is x from the highest part to the lowest part, after we get our answer, are we supposed to reverse? Is it a reverse or reverse it back?
Okay, that is saying x naught.
Because
Yeah, x
no,
1,
yes, yes, yes,
S
yes, yes.
S3. Yeah. So that gives us 1001. Since that is the order we've taken from the beginning, right? There's no problem with that. There's no problem with that.
Okay, sir.
Okay. Now, there are some other interesting examples in the lecture note online. Do we have to look them up again? Or we'll leave you to look them up. So if you've got any doubts, then we'll revisit, we'll look them up, together. What do you think? Or you want us to still look them up?
We should look them up.
Okay, we should look them up. Okay, let us consider another interesting example for the
Okay.
block codes before. I think with this we should be able to do syndrome decoding, and then Yeah, I think we should be able to do syndrome decoding, then move into convolutional codes. So let's assume we have a 7-4 code word. And in this instance, the generator matrix is given as XQ plus X plus 1. Right? So here we are to determine the parity check matrix and then design the code words, right? So we have not been asked to remain with the polynomial. We have been asked to design the parity check matrix and also the code words. And then the Hamming weights. So we have 3 things to do here. And all we have been given is that it's a 7-4 block code or cyclic code with the generator matrix. So here we already know that it's an NK code word. So it means the block length is 7. So we literally have bit position up to the 7th position. Does that make sense? So that's the block length. What I just said, does that make any sense for now?
Yes.
Okay.
Come again, Sabu.
Now we have 7-4 block code, and we have been given a generator matrix. Going by this, we know that the block length is 7. And if you recall our systematic code, we said the length of our systematic code is n. And the message bit k is the message bit length. And the parity is n minus k. So we know the parity here is 3, and the code length is going to be 7, where n is 7 and k is 4. So n minus k is going to be 3, right? So 3 plus 4 bits will give us 7 bits. So the code length bit is 7. So the generator matrix is going to literally give us a length of 7. That's where we are. That's where I'm going to. Right? Is that correct?
Yes, sir. Okay. Yes, sir.
Okay. Now, if that is clear, we already know how to design our generator matrix. So we have that the generator polynomial is the same as 1 plus g sub 1 x plus g 2 x squared all the way to plus g r minus 1 x to the power of r minus 1 plus x to the power of r. Okay, and we know that our redundancy here is the same as n minus k. And we already know it is 3 for that. So the generator polynomial equation has the highest power of what here? What's the highest power? Where this is r equal to 3. This is 4 minus 7 minus 4. That gives us 3. So the highest power is 3, right? Going by the formula, right? So
Yeah.
if that is true, we now know that our generator matrix is going to give us 1 plus g1x plus g2x squared plus g3x cubed. Because we know what that is. Right?
Yes, sir.
Now,
so that's, sir, going back to that, the GX, that means the last one here is supposed to be GX, GRXR.
definitely with this coefficient, right?
Yes, sir.
Now that we have this, so for the NK cyclic code, we already know that we have n encoded block length. But with this, now that we have the structure, we can now design a code, because g of x is given as this, x squared plus x plus 1. So going by this formula, it means that we have 1 plus x cubed, right? So if that is g of x, so what will be x g of x, which is this? That will be x times this, that will be x plus x squared plus x to the power 4, right? Now, what will now be our x squared g of x? That will be x squared plus x cubed plus x to the power 5. Then what will be our x cubed g of x? That will be x to the power 3 plus x to the power 4 plus x to the power 6, right? If g of x as given is this, then going by our formulation, we know g of x, for instance, then we can formulate this. Does this make sense for now?
So I can still go again.
Okay, now we have, what we want to do is to figure out the generator polynomial. Because we know that if we figure out the generator polynomial, it is the parity, the transpose of the parity times the identity matrix. So once we pull this out, it's just to get what? It's just to get P, okay? Because P will now be the transpose of this, right? So once we get P, then we know that the parity check matrix that we've been asked to investigate will be the identity matrix and the parity, right? And then we can now multiply whatsoever I want to do we can now generate the equations to develop our code words, and then we can get the Hamming weights. So if that is what we want to do, so we've been given the generator matrix and the generator polynomial, and we know that the generator polynomial is defined with respect to the redundancy as this. And we know that the redundancy here is 3, based on the fact that we have 7 to 4 code. And if we should plug that into this expression, so it means that we have 1 plus g1 of x plus g2 of x squared plus g3 of x cubed all the way. But we know g of x. So if we know g of x to be this, what could be xg of x? What could be x squared g of x? What could be s cubed g of x? Because for this generator polynomial, all of these coefficients are related to g of x, right? So we just developed a system of equation to show that, well, all of these put together, so if we plug in this into this, this into this into this, what are we going to get? Hello?
Yeah, we're here.
Okay, sir.
We are going to do the addition now, right?
Okay, you want to do the addition now. So if you do the addition,
Yeah.
what did you get?
Okay, I'm working on that.
So you're going to get something like 1 plus x to the 5 plus x to the 6, right? And that's not where we are going yet, okay? Or we are not adding yet. But we've developed some systems of equation, okay? So it means that I have my equation 1, 2, 3, 4, and 5. Now, there is another rule in this case. We have n block code. So it means the length of my code word will be what? My code word will contain how many bits?
That is 7.
7, yeah. So it means my code word will contain 7 bits. And for me to generate 7 bits, it must correspond with a generator matrix that will also span 7 bits, right? So it means that for me to be able to generate this, my g of x should be 1 plus x squared plus x cubed plus x to the 4 plus x to the power 5 plus x to the power 6. So that's 1, 2, 3, 4, 5, 6, 7. Isn't it?
Yeah.
Okay. But now, I already have developed a system of equations for my generator matrix, which is 1, 2, 3, 4. Now, my generator matrix will now be all of these put together as a row, right? So it means that what I'm trying to say now is that I want to develop my generator matrix. So my generator matrix now will now be g of x, g of x squared g of x, and x cubed g of x. So it means that this matrix will be the same as 1 plus x cubed, x plus x squared plus x to the power 4, x squared plus x cubed plus x to the power 5, x cubed plus x to the power 4 plus x to the power 6. And then once you represent with the bit representation, what are we going to get? Remember, it should correspond to our code word. My C is 7 bits. So it means that this is going to span the generator matrix is going to span x naught plus x to the power of 1 plus s to the power of 2 to the power of 3 plus s to the power of 4 plus s to the power of 5 plus s to the power of 6. So now it means that in this case, I have 1 to 3 bits. And this is x naught, x1, x squared is 0. So this 1, s naught, 1, s squared is 0, then x cubed is 1. So this is 1, 2, 3, 4. So it means that I have all of the bit position to x cubed, but x to the power of 4, s to the power of 5, s to the power of 6 is 0, 0, 0. Now for the next row of my matrix, I have x squared. X is 1, s squared is 1. Then s to the power of 4. So this is 0, this is 1, and this is 0, all right? So the other two will be 0, 0. Now here I have x cubed is 1, x squared rather is 1, s cubed is 1, s to the power of 4 is 0, then s to the power of 5 is 1, then this is also 0, then we'll have 0, 0. Now in this case, x1 is 0, x is 0, x squared is 0, but x cubed is 1, x to the power of 4 is 1, x to the power of 5 is 0, then x to the power of 6 is 1. So you now see that the system of equation aligns with the length of my code word. So we have not done anything irrational yet. Okay. Now that we have done this, we will now have to look up what we have. And our generator matrix should give us the parity check and an identity matrix. But when we look this up, well, this is okay. The first row is okay. The second row too is okay, but the third row does not follow my identity matrix. This bit is supposed to be 0, right? And the last row too does not follow because these last 2 bits are supposed to be 0. So what do you think we can do to pull this non-systematic representation to a systematic representation, where the parity base
Get the transpose.
Is it the transpose we do or the row transformation? Remember your matrices. But I think we want to perform row transformation. So by row transformation, it means that we have our generator matrix this way, which is this, and now we have to perform the transformation such that this bit position will turn to 0. So it means if we add row 1 and row 3, that's row 1 and row 3, this plus this will turn this to 0, and everything will be fine here. And for us to knock off these 2 bits, if we add row 1 plus row 2 plus this same row 4, so it means, let me think that's a little messed up. This is plus row 3. So this would be row 1 plus row 2 plus row 4. So it means our first row is just pretty good. This is 1, 1, 0, 1, 0, 0, 0. Then the second row is 0, 1, 1, 0, 1, 0, 0. And now for the third row, we said if we add row 1 to row 3, so 1 plus 0 is going to give us 1. 1 from row 1 to plus 0 in row 3 is going to give us 1. Is that correct, please? 0 plus 1 will give us 1. Then 1 plus 1 will give us 0. 0 plus 0, 0. 0 plus 1, 1. 0 plus 0, 0. So I think now this is in good shape. And then for the last, we add 1, 2, 3, 1, 2, 4, 1, 2, 4. 1 plus 0 is 1, plus 0, 1. 1 plus 1, 0, plus 0, 0. Then 1 plus 0 plus 1, 0. 0 plus 1, 1, plus 0, 1. And then the fourth now, 1 plus 0, 1 plus 1, 0. Then 0 plus 1 is 1 plus 1, 0. Now 0 plus 0, 0 plus 0 is 0. And then 0 plus 0, 0 plus 1 is 1. So now you see that we have been able to separate the parity check. Now, if we take a line all through this point, you see that this is an identity matrix where the diagonal is all 1. And then this is our parity. So it means we have a generator matrix now. Is that clear? Is this clear, please? Hello?
It's clear.
Okay.
Yeah, very clear.
Now that you agreed that this is clear, the next thing is to design the parity check matrix, which is H. And we know that it is the identity matrix and the inverse of the parity matrix. And we already know what the parity is here. The parity P is the same as 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1, right? So if we take the transpose of that, that's going to give us 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1. Isn't it? So the parity check matrix will now be, now the identity matrix will be 3 by 3. So that'll be 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So we already have the identity matrix for that. And then the transpose of the parity matrix will now follow directly. 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1. So we've been able to resolve the first point here. Is that clear, please? Is this clear? So it means that if, for instance, you decided to develop a block code that will run on this generator matrix or polynomial, so it means that in your encoder, you are going to program this into your encoder, while you are going to program this into your decoder. So it means the combinational logic or circuits in the encoder will interpret this, we have this encoded in it, while this will be in the decoder. Does that make sense?
Yeah.
Come again, sir.
So the generator matrix.
Sorry, sir. This the parity matrix, which is the H, like the first value, like the first matrix which you said 1, 0, 0, 0, 1, 0, and 0, 0, 1. Where did you get it from? Sorry, I was lost.
Did I miss out something here? Okay, which this the first 1, 0, 0?
Yes, sir. Yes, sir. Yes, sir.
So this is the identity matrix. Recall the formula. This is the identity matrix and the transpose of this. So it means this entire is the identity matrix, while all of this is the transpose of this parity. And recall, we got this parity from the generator matrix, since we've been able to separate this into a systematic code, so we can separate the parity bits from the identity matrix. And we know the identity matrix have a leading diagonal of 1, right? So you see that that's what makes it the identity matrix, because this leading diagonal is all 1, while all other elements are 0. Okay.
This is a 4 by 4.
Okay,
Yeah.
so this the leading diagonal is all 1, while all other elements are 0. That makes it an identity matrix. So we have the parity matrix, which is 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, and 1, 0, 1, 1, 0, 1. And like I mentioned earlier, the same parity runs in both the generator matrix and the parity check matrix. So the idea is that for us to be able to design the parity check matrix from the generator matrix, then we have to follow this formulation. Now, this is the formulation for the generator matrix, where we have the parity and the identity. So once we pull this parity out and take the transpose of it, then add the identity matrix, then we have the parity check matrix. So the transpose of this parity matrix is this, where we convert the row to column. So 1, 1, 0, this row is now this column, 1, 1, 0. 0, 1, 1, this row is now this column, 0, 1, 1. 1, 1, 1 is on this row is now 1, 1, 1 on this column. And 1, 0, 1 on this row is now 1, 0, 1 on this column, meaning we've taken the transpose of this. So the only thing we now need to do is to plug this into this expression. And once we plug this into this expression, you see this part is the same as this transpose, which is this. And what we just need to do is to patch up with the identity matrix. And you see the leading diagonal here is all 1s, right? So this is the identity matrix attached to this, which makes this the parity check matrix. Is this clear, please?
It's very clear. It's very clear.
Yeah, it's clear, but in our first identity matrix, we have a 4 by 4. Now it's not turning to 3 by 3.
Because we've taken the
It's a diagonal.
Yeah, this
Sir?
because we've taken the transpose, right?
Okay.
So how many
Okay.
rows do we have before? We had 1, 2, 3, 4 rows
3 by 4.
the
Yeah.
transpose. Before the transpose, after transpose, we have 1, 2, 3 rows, right?
Yeah.
Yeah.
Yes, sir.
So the size of the identity matrix is a function of the number of rows we have in the matrix in this case.
Okay.
And now the encoder will run this, while the decoder will run this. But one thing you should take note is this. There's one thing that is common with both the generator matrix and the parity check matrix, and that is this. So they understand the same bit sequence, so that this generator matrix can now be used to generate some specific set of code words. Okay? And those specific set of code words will be known by the parity check matrix because it's the same parity that was used to generate it. Do you understand? So it means that I cannot have a particular generator matrix running on my encoder and now have another parity matrix that matches another generator matrix running in my decoder. It will not decode what I generate efficiently. Does that make sense?
Yes, sir.
Yes.
Okay, so how do we now generate the code word? Because the next line of action here is to generate the code word, right? So how do we come up with the code word in this case? So I think that's the next thing we now need to do. So we need to develop the system of equations. So since we know this, now for us to be able to develop the how do I put it now? The parity bits, because now the code word is going to be my message bit plus my parity bit, right? Isn't it? This is what gives my code word. Now we already know we have a 4-7 code here, which is NK. So I know that my message bit is going to give me 4 bits. Now, my parity bit is going to give me 3 bits. So 4 plus 3 will give me 7. Okay? So, and I already know my parity matrix here, not the parity check matrix, the parity. Now, if I have this parity, then it means I can use this to develop my parity bits. This parity bits, what will be here? Which will be 3 bits. And the formula for that, to generate my parity bit, is now going to be my message bit times this parity. This will give me, so once I multiply my message bit by this parity, I'm going to get the 3 bits that will match my code word, that will match my message bits. Okay, but I know that this my message bit is 4. So I'm going to have M1, M2, M3, M4. I don't know what they are yet. They are more like random numbers. So I'm going to multiply it by this my parity matrix, which is P, to get this bit. So once I know this, I can now match it with this and I form my code word. Does that make sense? So that's the next space now. Can we move on? Can we move on, please?
It's not going to be very, very clear.
Okay. So it means that my parity bits will now be the same as my message bit times the parity. And from our design, we were able to generate the parity bit to be 110, 011, 111, and 101, right? And we know it's 7-4 code NK. So N minus K must be 3. So let's see if this is true. Now, if we're able to really provide an accurate generator matrix, and then it means this parity bit will give us the system of equations to generate these this sequence. So it means that I'm now going to have B1, B2, B3. I know it should be 3 bits. So this is going to be the same thing as my message bit, which I know it should be 4, M1, M2, M3, M4, which we now multiply this, which is 110, 011, 111, and 101. Okay? So by the time we resolve this, then we are going to have some system of equations. So B1, in this case, B1 will be this times this first row, right? B2 will be this times the second column. B3 will be this times the third column. So B1 will be this, that's M1 times 1 plus M2 times 0 plus M3 times 1 plus M4 times 1, right? So this will give us M1 plus M3 plus M4. Okay? That will give us our B1. And then B2 we follow directly M1 times 1, M1 times 1 plus M2 times 1, M2 times 1 plus M3 times 1, M3 times 1 plus M4 times 0, M4 times 0. So this will now give us M1 plus M2 plus M3, right? So don't forget it's modulo 2 addition. Then B3 is now going to give us M1 times 0 plus M2 times 1 plus M3 times 1 plus M4 times 1. So this will give us, this is 0, then M2, M3, M2 plus M3 plus M4. So we've been able to develop a system of equations for our parity bits. So we now know that if we have M1, M2, M3, M4 with B1, B2, B3, so this will give us 1, 2, 3, 4, 5, 6, 7 bits for my code word, right? Where we have the message bits and the parity bits. Now, how are we able to generate these code words? Don't forget, we got this from the generator matrix, right? So it means that you can literally design your system based on your polynomial or your generator polynomial. Okay? So the next thing is, how do we develop these code words? We have K to be 4, okay? And from our digital electronics, if the number of data word is 2, so how many possible distinct positions can we have? That's 2 to the power of K, right? So 2 to the power of 4, that would be 16. So we can have 16 possible code words in this, right? So that brings us back to logic, right? Binary logic. So we will now have our truth table. You remember all of those things, right? Hello? You remember the truth table for 8 bits. Now, when we have 2K is equal to 2, 2 to the power of 2, that's 4. So we have 0, 0, 1, 1, 0, 1, 0, 1. So these are the possible combinations in the truth table, right? You remember? Hello?
Yes, sir. Yes, sir.
So we now have to come up with the 16, right? Once we develop the 16 possible combinations, that will form our message bits. Okay? Now, you see, that will match this 4, M1 to M4. And once we have that, we can now use these formulas to multiply to add the different bits to get the parity bit for each of those code words. So this is what we need. So, and then B3 will be the same as M2 plus M3 plus M4. Okay. So here we have serial number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we already know when the first bit is turned on here. So that will be 0, 0, 0, 1. Then for the second bit position 2, this will be turned on 0, 0, 0. So we can just populate. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 4, 1, 2, 3, 4, 3, 4, 1, 2, 3, 4, 0. Oh, no. I think there's something here. There's 0, 0. Wait, no. Left. So this is going to give us 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0. Have I missed up something here?
The 2 is M3, M4, M3, M4.
I think I've missed up something here. So this is 0 here.
Yes, but okay.
I think I missed it.
Are we starting from the front or from the back?
No. This is
Okay, so
this
1 is M4.
Yeah.
2 is M3, M4.
I think I already spotted where the issue is there.
Be at number 8.
Yeah, this is 0, 1, 1. Because the first position is actually 0. So this is just serial numbers. So the first position is 0, all zeros, then all ones, then this would be 2, and this 3, this 4, this 5, and this 6, 7, 8, 9, 10, 11, 12, 13, 14. So when all the bit positions are found on, then that is 15. So the next thing to do is to apply. Now, you recall, this is just your regular truth table for 16-bit position. And from this, we know that we are going to have 16 possible code words. So with the generator matrix, we know that we can actually generate 16 possible code words. So our symbols can be matched to any of these code words. And once we transmit that, the parity check matrix, with the parity check matrix, we'll be able to decode these 16 possible code words. So then how do we now generate the parity bits? Now, the parity bits will be generated based on the parity matrix we pull from the generated matrix. And for this first bit, it's going to be 1 plus 3 plus 4. That'll be 1 plus 3 plus 4, that'll be 0. And for the second bit position, 1, 2, 3, 1, 2, 3, that's also 0. And for the third bit position, 2, 3, 4, that'll be 2, 3, 2, 3, 4, that's also 0. And for this, 1, 3, 4, that's 0 plus 0 plus 1, 1. Then 1, 2, 3, 0 plus 0 plus 0 is 0. And then 2, 3, 4, 0 plus 0 plus 1 is 1. Is that correct, please?
Start against that.
Okay, so let's do the third point. Let's do this third point. Let's change the color. Let's do this. I need to make this. Okay. So let's try this out. This third point. So what's B1? The formula for B1 is to add M1, M3, M4. So we're going to add M1. This is M1 here. For this is 0. M3 for this is 1. 0 plus 1 is 1 by modulo 2. Then plus M4. 1 plus 0 is what? 1. And then B2 is by this formula 1 to 3. So that will be M1, M2, M3. That's 0 plus 0 is 0 plus 1 is what? 1. 1. Then for B3 is M2, M3, M4. M2, M3 is 0 plus 1 is 1 plus M4, 1. So everything is 1, 1, 1. Is it clear?
It's clear now, sir.
Okay, so that's what we're going to do for all others. So I think here we have 0, 1, 0. Then we have 1, 1, 0. Then we have 1, 0, 0. Then we have 0, 0, 1. Then we have for 8, that's 0, 0, 0. 1, 0, 1, 1, 1, 1. I think this is 0, 1, 0. Then I think there's something wrong here. So for this, the fifth position, that'll be 0, 1, 1. Then this will be
Excuse me, sir.
1, 0. Go ahead, please.
Please, for number 4, B1 is supposed to be 1.
For number
Because
4. For
No,
number
it's 0.
0.
It's
B1,
0.
1, 3, 4. 1,
It's 0. 1 plus 1 is 0.
3. Then 0 plus 1 is 1. Then plus 1. 1 plus 1 is 0 for modulo 2. I hope that's clear. We drop the remainder, right?
it's clear. Sorry, I wrote something wrong. Sorry.
Okay. So how about for the 7th position? So that will be 1, 0, 0. Then for the 8th position, that will be 0, 0, 1. For the 9th position, 1, 1, 0. For the 10th position, 0, 1, 1. 11th, 0, 0, 1. 12th, 1, 0, 0. 13th, 1, 0, 1. Then 14th position, that will be 0, 0, 0. Then 0, 1, 0, 1, 0. Okay? So with this, we have been able to develop the code words using the generator matrix. So we can pull this out. So this all the code words now will be M1, M2, M3, M4, B1, B2, B3, right? So we just pull this out. So this 1, 2, 3, 4, 5, 6, 7, right? What about that? That's 1, 2, 3, 4, 5, 6, 7. Yeah. And then on and on. So we can literally populate this. So the next will be 0, 3 zeros, then 1, 1, 0, 1. Then this will be 0, 0, 1, 0, 1, 1, 1. Then this will be 0, 0, 1, 1, 0, 1, 0. Then this will be 0, 1, 0, 0, 0, 1, 1. Then this will be 0, 1, 0, 1, 1, 1, 0. And this will be 0, 1, 1, 0, 1, 0, 0. And this is 0, 1, 1, 1, 0, 0, 1. And this will be 1, 0, 0, 0, 1, 1, 0. This will be 1, 0, 0, 1, 0, 1, 1. This will be 1, 0, 1, 0, 0, 0, 1. And this will be 1, 0, 1, 1, 1, 0, 0. Right, this will be 1, 1, 0, 0, 1, 0, 1. This will be 1, 1, 0, 1, 0, 0, 0. And then this will be 1, 1, 1, 0, 0, 1, 0. And this will be 1, 1, 1, 1, 5. So with this, we can tell the weights. So the Hamming weight for this will now be all zeros. So the number of ones we have here is 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay. So with this, we've been able to address everything we need to address as far as the question is concerned. And should we transmit, we can equally test for syndrome decoding. I think we just have a few seconds. So let's assume, for instance, we want to perform syndrome decoding. So let's assume this is just an example, apart from what we have done. So let's assume we have H running in the decoder to be 1, 0, 0, 0, 1, 0, 1, 1, 0, 9, 0, 1, 0. Okay, let's put this to be 0, 0, 1, right? And then 1, 1, 0. So I have that. So this 1, 1, 0. Then here I have 0, 1, 1. Then I have 1, 1, 1, and then 1, 0, 1. So let's assume this was transmitted or received. We received 1, 1, 0, 1, 1, 0, 0. So we already know that syndrome decoding is received symbol times the transpose of the parity check matrix. So this is what happens in the decoder. So we want to check if what was received is received in error. So what do? So we just say, well, the syndrome will now be 1, 1, 0, 1, 1, 0, 0 times the transpose. So let's take the transpose of this. That's 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, and 1, 0, 1. Okay. So what do? We now multiply this times this plus this times this plus this times this. So the syndrome will be 1 times, can we say that together, please? So this 1 times 1 plus 1 times 0.
1 times 0, 1 time plus 1 times
0,
0.
times 0.
Okay.
Plus 1 times 1 plus
0 times 0.
1 times 0
1 times 0.
plus 0 times 1 plus 0 times 1. So that's the first, this first row times this first row, this row times this first column. Then we now do the same for the second column. That would be 1 times 0
times 0
1
plus
times
1 times
1
1
plus
plus 0 times 0
0 times
0
0
times 0.
plus 1 times
1
1
times 1.
plus 1
1
times
times 1.
1 plus 0 times 1 plus 0 times 0. And the last one will be 1 times 0
1 times 0
plus 1 times
1 times 0
1 times 0
plus 0
plus
times
0
1
times 1
0 1
plus 1
1
times
0
0 plus
plus 1
1
times
times 0.
1 1
Is it 1 times 1?
plus
1 1
1
yeah
times 1
Okay.
plus 0 times
0
1
1
0 times 1 plus 0.
0
plus
1
0 times 1.
So this 1 plus 0 is 1 plus 0, 1 plus 1, 0 plus 0, 0 plus 0 plus 0. So that's the first is 0. So this is 0 plus 1, that's 1 plus 0, 1 plus 1, 0 plus 1, 1 plus 0, 1 plus 0, 1. And then, so we already know there's an error here because it's not all zeros. So this is 0 again, times 0, plus 0, plus 0 is all zeros, plus 0, 0, plus 1 is 1, plus 0, 1, plus 0, 1. Now, since the syndrome is not all zeros, then it means there's an error. So what we now have to look up, we now have to come back to our parity check matrix to check the column that matches this. So we now trace. Which column matches this? 1, 2, 3, 4, 5.
the fifth column.
So this fifth column matches this. So it means the fifth bit must be in error. 1, 2, 3, 4, 5. So this must be in error. So what we now need to do is to change this bit to 1, 1, 0, 1, 0, 0, 0. So if we do that, so it means we are going to change this to 0. So it means that our third bits in all of this calculation, our fifth will now be 0 times 0, right? This will be 0 times 1, and then this will be 0 times 1. So once we check again, so what are we going to get? This is 1 plus 0. That's 1 plus 0, 1 plus 1. That's 0 plus 0 plus 0. So this reduces to 0. So the next now is 0 plus 1. That's 1 plus 0. 1 plus 1, 0 plus 0, 0 plus 0, 0. So this now reduces to 0. And then this is now 0 plus 0 plus 0 is all 0, 0 plus 0, 0 plus 0. So it's all 0. So there's no more error in the syndrome. So this is it. Now, this is how the parity check matrix is used to detect and correct errors. So you can now look at the improvement made on this by running an iterative process in the LDPC code. Does that make sense, please? Hello?
Sorry, I didn't get that, sir.
What didn't you get?
So after we've just discovered what the actual non-error code is, we are now going to use the LDCP.
No. I'm just, no. This has nothing to do with LDPC. So I'm just trying to tell you the improvement made. Okay, so this is what we have now for the Hamming code. And this Hamming code can only correct 1 bit error, right? It cannot correct multiple bit error. That's why we now, an improvement on this is what we have as your BCH code, your Rich-Solomon code. So your BCH code can correct for multiple errors, then your Rich-Solomon code can correct for burst errors. But beyond that, when we now have, a continuous bit string, for instance, like we now have in your, we're not talking about your compact disc or your CD or QRO codes anymore. We're not talking about actual real-time systems, your wireless communication systems, your LTE, your 5G, and all of that. We now need more sophisticated codes like turbo codes, convolutional codes, okay? And LDPC codes. You get what I mean? And we already know that LDPC code is an improvement on block codes. Block codes run on this principle where we use the parity check matrix to detect and correct errors in the decoder. Okay, this is how it does it. So we just saw the Hamming code perspective. So now you can look up the improvement made so far. So while conducting your research, you now have to think in terms of making improvement. And you can begin to look up things from, your turbo codes, your LDPC codes, and variants of your convolutional codes. Is that okay? I think we're already out of time. And since we already reviewed the entire process, I'll suggest you look up the examples we couldn't play with now should be the convolutional codes. So you want to look them up in the lecture notes we have online. So we'll move to the next topic in our next class. And if you've got any doubts in the worked examples on convolutional codes, then we could address them in the question and answer session in our next class. Is that okay?
It's okay, sir.
Okay, so I think for now we'll say we've concluded our discussion on channel coding. So any question for now? Okay, so I think the silence speaks a lot. It means you understand everything we've done so far, isn't it? Is it? Can I get an affirmation?
Yes, I will go through the course.
Yes,
Okay.
sir. Yes, sir. We're fine with
Okay.
it.
Okay,
Yes,
so
sir.
I think I'll say goodbye for now. We'll see in our next class.